Thank you for inviting me for this AICTE ATAL sponsored online FTP on global challenges in sustainable manufacturing using 3D printing and design. And my topic is concepts of various 3D printing technologies. I am Joseph Mathew, Managing Director of Insta 3D Technologies, and we are situated in Coimbatore. So let's get into the topic. You know what is a manufacturing process, and the manufacturing process is of two types. First one is additive and the other one is subtractive, and there are few other manufacturing processes involved, I mean, getting introduced nowadays. So let's start with what is additive and subtractive manufacturing process. So as we see, subtractive manufacturing it involves the removal of material from a raw material block or any wood or any raw material. So by removing material, we are getting the final end product. So this is called subtractive manufacturing, and it can involve many processes like turning, milling, drilling, EDM, grinding, etc. Even CNC, everything is comes under subtractive manufacturing process. So when we go to additive manufacturing process, it refers to a process by which the 3D design data is used to build a component layer by layer by depositing material one over the other. As you see, a cube can be 3D printed or additive manufactured by depositing or building layer over the adjacent layer. So you can get the final end product. So we must see the difference between additive and the subtractive manufacturing process. As we see, in subtractive manufacturing process, the raw material is being machined and the end product is arrived. And there is many more scrap or waste involved in subtractive or conventional manufacturing process. But when we see with additive manufacturing process, the material is used in controlled manner, or the actual material which is required for the product is used, and the scrap or waste involved is very less. So it's a green technology where you can reuse the material as well. So it's the additive manufacturing is found advantageous over the conventional or subtractive manufacturing process in many aspects. So let's start with 2D printing. As you know, 2D printing is the conversion of a digital file into a physical file. So you can convert a digital 2D format file into you can get a physical form of like taking Xerox of a paper or a printout of a PDF. It is called 2D printing. So what is 3D printing? It is also the conversion from digital file to a physical model. In this, the digital file can involve any type of file like STL, OBJ, WRL. So there are many 3D files available in the CAD, and these 3D files can be converted into physical form using a 3D printer. So this 3D printing is a stacking of 2D prints. So these 2D prints are stacked up one over the other to form a 3D object. This is called 3D printing. So let's talk about the technical part of 3D printing. It is also called rapid prototyping, which is the automatic construction of physical objects using additive manufacturing technology. There are many other terms for rapid prototyping, which is called solid freeform fabrication, digital fabrication, automated freeform fabrication, solid imaging, layer-based manufacturing, etc. So 3D printing is one of the commercial term which is provided to rapid prototyping. And we are going to look at the different types of 3D printing technologies, and these types of the different types of 3D printing technologies is differentiated based on the building mechanisms, its price point, different materials used in the technology, and the applications involved in this 3D printing technology. So this is the classification of 3D printing technology. First one is material extrusion, vat polymerization, powder bed fusion, material jetting, binder jetting, and powder bed fusion of metals. So let's see about FDM or triple F technology, that is the material extrusion family. So in FDM technology, the FDM means fused deposition modeling, and triple F means fused filament fabrication, which is an additive manufacturing process that belongs to the material extrusion family. So in FDM, an object is built by selectively depositing melted material in a predetermined path layer by layer, and the materials used in FDM technology is thermoplastic polymers, and it comes in the form of filament. So these thermoplastic polymers can also be reused again and again to create the 3D printed parts. And this FDM technology is the most widely used 3D printing technology, and it represents the largest installed base of 3D printers worldwide. So you can see many FDM 3D printers worldwide, and this is the first technology which people are exposed to. So people can rely on this FDM technology or triple F technology easily, and they can get their 3D printed parts done using FDM technology. And the designer who is working with FDM technology should keep in mind about the capabilities and limitations of the technology when fabricating a part. So let's move on to the working principle of FDM process. So this has a spool of thermoplastic filament which is loaded into the printer. As you see, you can see a blue color filament spool, and this is in the wire form. This is a thermoplastic material which is loaded into the 3D printer. And once this is the extrusion block, and once the extrusion nozzle reaches its desired temperature, the filament is fed into the extrusion head. This dark gray color is the extrusion head, and the filament is fed into the extrusion head after heating the extrusion head, and there the thermoplastic melts around from 200 to 300 degrees based on the filament which you are using. So this extrusion head is attached to a 3-axis system, X, Y, and Z axis. So you know 3D printer has 3 axes, which is called X axis, Y axis, and Z axis. And this melted material is extruded in thin strands based on the nozzle size of the 3D printer. The basic material filament size will be 1.75 mm and 3 mm in diameter. So this filament size is fed into the extrusion nozzle, which has a varying nozzle sizes from 0.2 mm to 1.5 mm. So this nozzle, the finish of the 3D printed part depends on the size of the extrusion nozzle, and also the layer resolution, everything depends on the extrusion nozzle size. So the extrusion head is attached to the 3-axis system, and the melted material is extruded and is deposited layer by layer in predetermined locations as mentioned in the G code. G code is something which is inputted into the 3D printer which it involves the various extruding temperature, the coordinates of the 3D printer motion, everything it involves. So this G code is inputted into the 3D printer, and the FDM 3D printer works as per the G code. And this deposition of layer by layer in predetermined locations, it is cooled by cooling fans, and which is attached to the extrusion head. And this formation of 3D printing process involves formation of outer shells, and the infill parameter is used to fill the inner part of the product. So you can see two materials are being used in this FDM process. One is the build material, and the other one is support material. This build material is the main part which is getting 3D printed, and the support material is used to support the overhang features which is available in the 3D printed part. So this supports are of two types. One is breakaway support material, and the other one is water soluble support material. So, what is breakaway support structures and what is water soluble support structures? You need to know the difference between these two things. So, breakaway means you can just break it away, or you can just remove the support from the main part. So, the breakaway support structures, which is called BAS, uses the same build material as support structure. So you just need only single filament to create self supports for creating that 3D printed part. And when you use water soluble support structures as shown in the image, you need to use two nozzle heads, so that one uses build material and the other nozzle uses support material. So you can see the image here. Uh, the left nozzle extruder uses build material, that is the dark blue color, and the right nozzle uses the support material, which is the light blue color. So this support material is water soluble and it dissolves in hot water. So you can just put the 3D printed part after finishing the 3D printing process. You can just put it in hot water, so that the water soluble support structures, preferably the support structure which is used is PVA material, and this material just dissolves in hot water, or in even in warm normal water. So the final part is formed. So this is the basic principle of FDM process. And let's get into the parameters involved in FDM process. As you see, there are various parameters like layer height, infill ratio, infill pattern, shells, even speed, temperature, bed temperature, cooling fan speed. Everything can be adjusted in the 3D printing software, and this adjustment is as per the material which is used for the 3D printing process. So you can vary the layer height from around 50 microns to 600 microns based on the nozzle size. Mostly all the 3D printers will be installed with zero point 0.4 mm nozzle, and the material which is used is 1.75 mm, and the layer height achievable in a zero point 0.4 mm nozzle is from around 100 microns to 300 microns, which is around 75 percentage of the nozzle size accounts to the layer height. So 75 percentage of this 0 0.4 mm nozzle will be around 0.31 or zero point 0.3 mm, which is nothing but your 300 microns. So this layer height can be varied in 3D printing softwares. Also the infill ratio. You need to know what is a shell and a infill first. So as you see in this image, it is a cube. This has an outer perimeter which is called the shell, and these shells can be varied in the 3D printing software. You can provide 2 shells, 3 shells, 4 shells, and the shell width will be the width of the size of the nozzle. If 0.4 mm nozzle is used, the one shell thickness will be 0.4 mm, and if you are using 2 shells, it will be 0.8 mm in thickness. So the shell thickness can be varied in the 3D printing software. Also the infill ratio can also be varied. You can just manufacture the cube in a total solid form, or in a 80 percentage infill, or in a 25 percentage infill, or even a hollow cube can be formed using FDM 3D printer. It's like the option is available in the software, where you can vary the infill ratio from 0 to 100, so that you can define how much amount of material is inside the solid block. So you can vary the infill ratio based on the application which you are using. So if you are going for just for a prototyping purpose, you can go for 10% or 25% infill, which is an optimal infill ratio for any 3D printed part. And if you go with functional prototyping, so if you are going to use the 3D printed part as a functional product, you can go with 80% or 100% infill. So even the infill pattern can be changed in a 3D printing process, FDM 3D printing process. And you can ask, what is a infill pattern? So this is a grid type infill pattern. This crisscross lines which is involved inside the 3D printed part here in this crisscross lines is called infill, and the pattern in which it's generated is called infill pattern. You have many infill patterns like grid, rectilinear, rectangular, triangular, cubic, then honeycomb structures, honeycomb infill patterns are also available. So there are many infill patterns available online in the software. So next we can see about warping effect and layer adhesion of FDM 3D prints. So this warping effect is something which is an error caused in FDM 3D printers. So this warping effect is shown here in this image. So you can see a 3D printed part which is slightly bent. So this warping effect happens when just imagine if you are 3D printing in a FDM 3D printer, the first layer is formed and each point in the first layer cools at different cooling points. So the first laid material will cool faster than the latest laid material, and this different cooling points makes the second layer to pull the first layer upwards. So you will get a internal stress inside the 3D printed part, which makes the product to warp, and it is shown here in the image. And in order to avoid the warping effect, you can just avoid flat 3D printing of flat surfaces, and sharp corners can be avoided and fillets can be given in the 3D designs in order to avoid the warping effect. And even you can provide extra material in the warping side, so that you can just cut away the extra material which is provided. And these kind of techniques or solutions are available to minimize the warping effect. And let's get into the layer adhesion. So this layer adhesion is something which needs to be studied in detail in FDM technology. Probably the layer adhesion of FDM technology is bit minimal in the Z direction, whereas layer adhesion of XY in the XY axis is good. So if the z-axis height increases of in the 3D printed part, the product will be less strong. And if it has a good length, or it has a good amount of volume in the XY part, the adhesion will be better, and even the strength of the 3D printed part will be better. So minimal Z height, the 3D printed FDM part will be very good. It is also same for the other processes as well. So there are typically three characteristics which needs to be studied in before 3D printing. And the first one is avoid large surface areas, and the second one is minimizing supports, and the third one is minimizing the Z height wherever possible. So these three are the main characteristics when considering 3D printing technology. So these are the materials used in FDM technology. It starts right from basic materials or commodity commercial materials such as PLA, ABS, HIPS, polystyrene, PP, etc. And it can reach up to around 450 degree Celsius. So you can print around till peak and PEI materials, and even Alta material is also being 3D printable. So these FDM 3D printers, desktop or industrial grade 3D printers, can reach up to 450 degrees. So you can print almost all the thermoplastics available in the market. So these desktop 3D printers which we are using regularly in the regular market, can process PLA, ABS and nylon easily. Even TPU is printable using desktop 3D printers, and higher grade 3D printers are required. Industrial grade 3D printers are required to print the peak and PEI materials, since it needs a steady ambient temperature inside the machine. So the machine should be of industrial grade, and the materials used in the machine should be of higher quality. So only then you can reach up to the peak and PEI materials. So these are all literally thermoplastic materials which we can reuse it anytime. So looking at the benefits of FDM technology, FDM is one of the cost-effective method of producing custom thermoplastics, and the lead times are very short because it is very much highly available in the market, and wide range of materials is available for both prototyping and functional applications. The limitations, each technology has its own limitations. The FDM has low dimensional accuracy when comparing with the other 3D printing technologies. So it's not suitable for parts with intricate details. Very small detailings cannot be achieved out of a FDM 3D printer. But by changing the nozzle size or reducing the nozzle size, you can reach up to 1.08 mm details easily in a FDM 3D printer, but it's a bit difficult practically. So these FDM parts have visible layer lines. So extra post processing is very much required for a smooth finish, and which is a disadvantage in FDM 3D printing. This post processing techniques involves sanding, even acetone vapor smoothing is can be done to a ABS 3D printed part so that you can get a smooth surface finish. And you can also go with epoxy coating of a FDM 3D printed part so that you can get a smooth surface finish. And also the adhesion feature will enhance when we go with this epoxy coating. And the layer adhesion mechanism makes FDM parts inherently anisotropic. So let's move on to the next one, which is called VAT polymerization classification method. And under VAT polymerization, you have three kinds of technology. First one is SLA DLP and SLA LCD. So SLA is stereolithographic apparatus, which is one of the first found 3D printing technologies in the 1980s. And the DLP is something a successor of SLA, digital light processing. And SLA LCD is the latest technology which is available in the market. So let's see it one by one. So let's see the working principle of a SLA first. You have a build platform here. The black one is the build platform, and the source of um, curing method is the laser, and the laser source is indicated in the top and it's in yellow color. And you have a resin tank, and the resin which is used, resin which is in liquid form, is UV curable, and this movable build platform can move from top to bottom. So this is called top top to bottom approach. So this laser source using the XY scanning mirrors just focuses the laser source onto the curable resin, so that once the laser source is focused onto the resin, the resin is cured, and the resin curing wavelength varies between few resins. It's mostly in the wavelength of 405 nm, and these UV curable resins are thermo setting plastics, and which cannot be reused regularly. So it cannot be reused at all. And so the failures involved in SLA process can be should be reduced in order to make the 3D printed part effectful. So the process involves by creating a 3D CAD model and converting it into a mesh file, which is called STL file. And then the STL file is sliced into n number of layers based on the layer height, which is given in the software. And this sliced file is being inputted into the 3D printer, which starts creating the 3D printed part layer by layer. So this build platform first will be in the top position, so that the laser source just focuses on the curable resin and makes the first layer, just scans over the resin and according to the contour of the 3D printing model available, and then it moves step by step into the bottom and the total 3D printed part is formed. So as I said, there is a difference between SLA and DLP technology. SLA technique uses laser as the light source, whereas DLP technology uses digital light projector as the normal projector as the image light source. So as you see in SLA, the laser will be a pointed one where the curing will happen very slowly. Whereas in DLP method, the whole contour of the or whole cross section or the whole contour of the 3D printed model or any layer will be focused onto the platform, so that the whole layer will be cured at once at regular intervals. If you are giving 8 seconds as the focusing time or curing time, so in 8 seconds the whole one layer will be produced. So as many as components you keep in this DLP 3D printer, you can form the whole layer at once. But in SLA technology, it is similar to the FDM principle, like it forms the shell and it forms the infill, everything. So DLP is a bit faster than SLA technique, but it's like Adobe and Photoshop and Corel Draw. In Photoshop, you'll get a pixelated image, whereas if, when working with Corel Draw, you'll get a clear, sharp image. So it's the basic difference between Corel Draw and Photoshop, and the same applies here. In SLA, the accuracy and dimensionally, the part will be stable and it will be perfect. In DLP method, it's a little bit less when compared with SLA technology. And you can see there are two approaches which is shown here. The DLP uses bottom up approach and the SLA uses top bottom approach. These approaches varies in different machines, and this uh, bottom up approach is mainly used in desktop machines. And when using bottom up approach, the printable area gets reduced, whereas when using top bottom approach, the printable area will be in 1 meters. You can also print 1 meter object easily in a top bottom approach machine, whereas you can go up to around 200 or 300 maximum in a bottom up approach method. So even the technologies used now mostly uses the bottom up approach, where the this thing 3D printing size is very less in nature. So this is the SLA LCD type 3D printer, which is a new kind of 3D printing evolution in the SLA method. You will have a LED screen, LCD screen here, and a LED projector light here, and you have condensers all over the part. And the preferable method which is used here is a bottom up approach. So the 3D printable area will be bit lesser when compared with the other SLA machines. And the LCD screen projects same like the DLP projector. At once the whole layer will be cured at once. So the 3D printing process in SLA LCD is almost similar to that of the DLP 3D printer, and only difference is there we are using a digital light projector, and here we are using LCD screen as the light source. So here the supports, you can see how the supports are formed in a SLA 3D printed part, and these supports are of various types like pillars, tree-like supports. Everything can be detailed in the 3D printing software, and these supports can just be cut with a plier and be finished with a sanding grit paper, so that you can finish the final 3D printed part. And it is kept at a angle in order to get a proper 3D printed part. If you are laying it flat, there are possibilities for warping. Similar to warping, the error which is happening here in SLA technique is curling, and it can happen in SLA, LCD and DLP methods. So they will orient the part in a 45-degree angle in smaller machines. So as we come into the printer parameters, it is mostly fixed by the manufacturer, and the whole printer parameters have been predefined in the 3D printing software. The only parameters which we can change is the layer height, support details, and the build size in the 3D printing software. And as I said, similar to warping effect in 3D FDM 3D printing technology, the error which is happening here in SLA is called curling. So when the first layer is formed, the uh, resin is cured, and when the curing of second layer takes place, the second layer, when it starts curing, it pulls the first layer upwards. So curling happens, similar to the warping effect in FDM 3D printers. So this curling can be reduced similar to that of the by keeping it in a 45 degree angle in 3D printers, so that curling can be eliminated. And the layer addition of a SLA 3D printed part is very high, so that you can literally build any component with high dimensional accuracy in a SLA 3D printer. So layer addition is not an issue in SLA technology. There are various materials that are used: thermosetting plastics, which is a normal resin, castable resin, dental resin, flexible, transparent, tough. Many resins are available in SLA technology, and these resins are bit higher in price tag when compared with FDM materials. Normally, 1 kg of normal resin will cost you around 7,000 Indian rupee, whereas 1 kg of PLA material or ABS material, which is used in FDM the printer, it will be around 1,500 to 2,000 based on the quality of the material which we are using. So these resins which is involved in SLA 3D printer, it has wide range. Like you can use it for jewelry purpose, investment casting purposes, dental purpose. Even flexible resins are available, and transparent 3D printing resin is also available in SLA. And to get the maximum transparency out of a 3D printed SLA part, you need to sand the 3D printed part so that you can get a fully transparent part using a SLA 3D printer. Even tough resins, which is used for functional prototyping, can also be used in a SLA 3D printer. So let's move on to the pros of SLA 3D printer. It's one of the most precise 3D printing technique, and any detailed feature can be finely created using a SLA 3D printer. That is, thin walls and sharp corners, etc., can be easily generated, and complex geometrical shapes can also be easily manufactured using a SLA 3D printer. And the layer thickness can vary from around 20 to 25 microns to 250 300 microns. So this low layer thickness is reachable in any SLA 3D printer, and the output of the SLA 3D printer is very highly dimensionally, it's very accurate in nature, and the print surface is very smooth, whereas in FDM technology it's bit coarse in nature. You can see the layer lines are very much visible, and the build volumes are higher without sacrificing the precision, whereas in FDM technology, if we go with a desktop normal machine, the precision, it affects the build increase in build volume will can affect the precision of the 3D printed part. So when we go into the cons of the SLA 3D printer, 3D printing of SLA takes a long time. Maybe a few support structures, many overhangs and steep slopes require support structure during the building process. So it has a possibility to collapse during the printing or curing phase. So we must study the 3D print 3D design perfectly, so that you can 3D print it perfectly according to your application. And the resins are very fragile, and it is not at all used for functional prototyping, but few resins, which is a mixture of ABS and certain plastics, you can use it for functional prototyping. Like tough resins can be used for functional prototyping. The other resins are just used for normal prototyping purpose. And it has limited material options, and the color choice is very minimal in case of SLA 3D printer. So it is you cannot get an aesthetically good part out of a SLA 3D in terms of color and material. You cannot, you have no wide choice of wide range of materials or color like in FDM technology. And the SLA 3D printing cost is also very high because of the material cost and the machine cost which is involved. So let's move on to the next technology, which is powder bed fusion using polymers, and the technology's name is selective laser sintering, SLS. So this is a SLS 3D printing working principle. So you'll have a powder feed piston, the powder, the polymer powder, which is stored in this bin. It has a powder feed piston which will be moving from bottom to up direction, and there will be a leveling roller which is available in the 3D printer, which rolls the powder onto the build chamber. This is the build chamber which is in the center, and this is the powder collection piston or powder feed piston which is placed both sides of the build chamber. So the roller rolls fine layer of powder onto the build platform and goes to the other side of the 3D printer, the roller. Or here it has only two parts. One is the powder bin, and the other one is the build chamber. Here the roller rolls the powder onto the build chamber and then rolls back to its original position. So here the source used is laser. CO2 lasers can be used here, and this lasers using the lenses provided and the scanning mirror, it focuses on the build platform so that the powder gets sintered and the whole part is formed. So it starts sintering layer by layer, and the whole part is getting 3D printed. So it's a easy technique, but the working atmosphere and the material management is a bit difficult in case of SLS technology. So there are wide range of materials which is available in SLS technology, and it is mainly used for the purpose of functional parts. You can print highly strength materials, 3D printed parts using SLS technology, and the base material used here is powder, which is a different kind of material which is used when compared to FDM and SLA, and it is still it is still at the industrial scale, and commercial machines are very much uh, lower in availability, and the starting range of 3D printers will be around 20 lakhs. So desktop machines are very much it is like availability is very low. So let's move on to the characteristics of SLS technology. There are no support structures which is required while building a 3D printed part in SLS technology. You can ask why. It is because of the powders which acts as the self support. So as you see here, so this is a overhang here, and the powder below acts as a self support. So you can just take the part out and remove the dust the powder out of the 3D printed part. So separate support structures aren't required for SLS technology. The layer height can vary from around 70 microns to 300 microns, and the layer adhesion is finally better than FDM technology, and lesser than the SLA technique. SLA technique has the most layer adhesion in comparing all the technologies. Here, the 3D printed part will be porous in nature. So this is a SLS 3D printed part, and it will be porous in nature. You can see many pores in the 3D printed part, and in SLS technology, there are few errors which is happening, which is called shrinkage and warping. Warping is similar to the warping effect in FDM technology. It happens due to the internal stresses produced in the 3D printed part, whereas shrinkage happens due to the sintering of powder. And there is another disadvantage, which is called over sintering. Overexposure of laser light onto the powder with intricate details can lead to over sintering, and the whole 3D printed part or 3D printing the holes will be difficult in SLS technology. Few holes which is around zero point 0.8 or 1 mm in diameter with a large thickness of wall, there the chances of sintering is very high. The over sintered part uh, will ruin your 3D print. And the powder removal, uh, when you build a part which is fully enclosed in nature and it has a hollow region inside the 3D printed part, you need to remove the extra powder which is available inside the 3D printed part. So you need to provide few escape holes so that the 3D printed the powder which is encapsulated inside the 3D printed part can be taken out. So when designing, we must take care in providing escape holes for hollow 3D prints. So these are the materials which is available in SLS technology. First one is polyamide, which is the nylon material, PA12, PA11, PEEK. Even polyamide powders, which can be mixed with carbon fiber, glass fiber, aluminum, etc., can be used to improve the brittleness, and it can have highly anisotropic behavior. So as I said, you have it is the 3D printed SLS part is porous in nature, so it can absorb much of moisture from the environment. So literally a 3D printed SLS part can absorb moisture from the atmosphere. So a few the 3D prints will be sintered later on after the 3D printing process to enhance the mechanical characteristics of the 3D printed part. Even the dyeing process can also be done in a SLS 3D printed part, so that you can vary the color of the 3D printed part. Since it has porous nature, it is easy for dyeing. So when looking at the advantages of SLS 3D printing technology, the dimensional accuracy is very good, but the availability of material and the availability of lower range, lower price tag machines is very less in SLS technology. So it's a bit difficult for the normal people to reach out to this technology. So next process is the material jetting or drop on demand 3D printing technology, DOD, which is called, you can see DOD here, which is called drop on demand. So in this, the extrusion head has a numerous nozzles which inputs material through the nozzles available in the head. There will be around 1,000 nozzles available in the 3D printing head, and there is a UV light, which is UV light source, which is provided as you see here. So as the nozzle ejects material onto the build platform, the UV light which is provided in the extrusion head cures the raw material which is ejected from the nozzle. So hence the 3D printing takes place layer by layer. After layer by layer deposition of material, the 3D printing part is formed. So this nozzle can handle various materials, which is very strong in nature, which is flexible in nature. Even support materials can also be inputted using the nozzles available in the head. So this is a material jetted part, or the main 3D printer used for material jetting is polyjet 3D printer. You would have known it is a very famous 3D printing technology coined by Stratasys. And as we see, the print head has inkjet print heads, uh, which is fed with the raw material, and you will have a UV curing light, and it moves in the X and Y directions, and the build platform moves up and down. So let's come on to the characteristics of material jetting 3D printer. So you can handle multi-material printing in a material jetting 3D printer. Full color printing is also possible using material jetting printer. Dissolvable materials can also be printed using material jetting printer. That is solvable support materials can also be 3D printed. The layer height can be achieved from 16 microns, which is very lesser when compared to the SLA technology. Even 16 microns is achievable using material jetting technology. And there are two types of finish available, matte and glossy, which we are going to see it in detail. So first is the multi-material printing capability of a material jetting 3D printer. As I said, there are number of nozzles involved in the print head. The nozzles can mix materials and provide you various materials with different shore hardness. So you can vary the shore hardness of the material using the nozzles available in the 3D printer. So in PolyJet 3D printer, there are basically two materials available. One is the Vero material and other one is the Tango material. So this Vero material is quite hard in nature, and the Tango material is flexible in nature. So mixing these two materials, you can vary the shore hardness of the output 3D printing part. So as you see, this is a remote which is 3D printed. The outside black part is flexible in nature, which is with a varied shore hardness, and the white part is the Vero clear material, and it is hard in nature. So in order to get the cushioning effect, we have 3D printed it in flexible one with the one with good shore hardness. So the shore hardness can vary from A to D, and this kind of 3D printing, there are many researches happening in PolyJet 3D printing technology, and since it can handle multi materials with versatile materials can be handled using a PolyJet 3D printer. Even full color printing is possible, as mixing is possible. It works similar to your the 2D printer, color printer. So full color printing is also possible in this polyjet or DOD technique. And you can see there are two finishes which is shown. The left side finish is called glossy, and the right side finish is matte. So you can ask me what is the difference between a matte finish and a glossy finish. So this in glossy finish, wherever support structures are required, their support structures will be 3D printed, and the rest of the 3D printed surface will be glossy in nature. Only where the support structures are getting generated, there the finish will be little matte in nature. Whereas in matte surface finish, the whole 3D printed part will be encapsulated in support structures. So you will get a matte type surface finish. So generally the matte type surface finished 3D printed part is is costlier than the glossier one. So as it involves high volume of support requirement for creating a matte finished 3D printed component, the cost will also go high. So these are the materials used: standard, flexible, simulated PP, simulated ABS, castable, transparent, high temperature resins, and even medical grade materials are also used in DOD or polyjet technology. These each material has its own advantage and disadvantage, and you need to study on where you are going to apply the 3D printed part, and according to that you can choose the material from the list. So looking at the benefits of material jetting, it can provide smooth paths with surfaces comparable to injection molding parts, and it's very dimensionally accurate in nature. And parts created here has homogeneous mechanical and thermal properties, and multi-material capability of the material jetting 3D printer. It can enable the creation of accurate visual and haptic prototypes. Many haptic prototypes can be achieved out of a DOD technique 3D printer. There are certain limitations. It's kind of very costly in for procuring the 3D printing materials, and it is mainly used for non-functional prototypes, and it has poor mechanical characteristics. Certain materials has poor mechanical properties, and it is generally photosensitive in nature and toxic in nature as well. Few materials used in MJ technology is a bit toxic in nature, and basically, for a research purpose, this is the best machine which I have personally been exposed to. So next one is the binder jetting 3D printing technology. So in this, it is similar to that of the material jetting technique. It also uses inkjet print heads, where the binder is being inputted onto the build platform using the print heads available in the 3D printer, and these binders is laid onto the powder which is filled in the build platform, so that the binder just binds the powder together so that you can get the 3D printed part. So this is the 3D printed using a binder jetting technology. So here it can also print it in full color. Models can also be 3D printed using binder jetting technology. Even bigger sand molds can also be created using binder jetting technology. The materials used here is silica sand, sandstone, stainless steel, bronze inflated, stainless steel with sintered technique, inconel alloy, tungsten carbide can also be used in binder jetting technology. So in this technology, it's almost similar to that of the SLS and DOD technique. It is the combination of SLS and DOD technique. You have a bin which is provided with material powder, and the roller rolls the powder onto the platform, and the binder is being inputted from the extrusion head, and this binder joins the powder to form the whole 3D printed part. So in case of overhangs, support is not required like in SLS technology. The powder itself acts as a support material. So we need to stress the usage of supports, you need to take care to get to give the escape holes in 3D printed parts so that you can remove the excess powder outside. So the layer height can vary from 100 microns to 300 microns. It can also be used to produce large scale 3D printing projects like sand casting cores and molds, which is shown in the image here. And metal binder jetting is also possible, which is similar to the plastic binder jetting. This in metal binder jetting, you can get metal parts out of a 3D printer in low cost manner. When you go for full DMLS or SLM technique, the cost involved is very high, Whereas when you need a mechanically unstable 3D printed prototype, which is 3D printed in metal, you can go with metal binder jetting technology. Here, we use two kinds of process to enhance the characteristics of the 3D printed part. One is infiltration technique and the other one is sintering. Once you binder jet or you produce a part out of a 3D metal binder jet technology, you can take the part out and you can load it into a furnace and enhance the properties using sintering technique. Or you can also infiltrate bronze material onto the 3D printed metal part, so that the pores inside the 3D prints gets filled with bronze material, so that you can get a good stable mechanically stable 3D printed part. So here you can see the stainless material which is being which can be sintered, as well as bronze infiltrated stainless steel can also be used in binder jetting technology. So the benefits are the binder jetting produces metal parts, and full color prototypes can be produced at fraction of cost when compared to DMLS technology. DMLS is direct metal laser sintering, which is a metal 3D printer, and the cost involved is very less when compared to those processes. It can manufacture very large parts in available in meters, like 2 meter, 3 meter machines are also even available for binder jetting technology, and even complex metal geometries can also be produced out of a metal binder jetting technology, and it is very much suitable for low to medium batch production. So you can low volume manufacturing production is possible using binder jetting process. And the limitations is that you have lower mechanical properties when compared to DMLS and SLM technology, because of the high porosity of the 3D printed part. And to reduce the porosity, we are sintering or infiltrating the part with other materials. And intricate details cannot be printed using a binder jetting 3D printer, and the part will be very brittle in their normal 3D printed green state, and may fracture during post processing. So care should be taken that it should not you should not put the part down, so it can get damaged easily. So until sintering and other post-processing techniques, the part will be very brittle in nature. And compared to other 3D printing process, it offers very limited material selection as well. So the last one is powder bed fusion using metals. SLS is using polymers, and this DMLS, SLM, and EBM technique is using metals. So we are using metal powders in DMLS, SLM, and EBM technologies. So this DMLS SLM is called direct metal laser sintering. DMLS is called direct metal laser sintering. SLM is called selective laser melting. EBM is called electron beam melting. So these are various 3D printing technologies which is for which the raw material is used is metal. So this is a metal 3D printed part which is shown in the image. So any complex structures can be easily 3D printed using a metal 3D printer, which cannot be done using a conventional 3D printing technique. And it is very much similar to that of the SLS 3D printing technology. It involves the same working principle of SLS technology, where the difference between DMLS and SLM is that DMLS uses different materials with different melting point. So it's generally there are different melting points. Alloys can also be 3D printed using DMLS technique, whereas in SLM technique only single homogeneous material can be 3D printed in SLM technique. EBM technique, EBM 3D printing technique involves usage of controlled atmosphere to 3D print metal parts. So it's same as the SLS technique. There is a powder bin which is the 3D printing metal powder, and it is being rolled onto the platform, 3D printed platform, and the platform moves up to down, and the laser focuses on the as per the contour or cross section of the 3D printed model, so that the final 3D printed component is obtained. And here there are support structures that is developed in DMLS and SLM techniques. These support structures can be machined out and taken out after the 3D printing part is taken out of the 3D printer. So you can see the support structures here. So these support structures can be um, machined out after taking out of the 3D printer. So here it is very much suitable for small batch manufacturing or low volume production, and it is highly recyclable in nature. The dimensional accuracy is very high. Even layer height can be varied using in the material 3D printing process or software. And certain hollow sections and lightweight structures can also be 3D printed using metal printing technology. So these are the various materials used. In this, the alloys are 3D printed using DMLS, and normal materials, single material, homogeneous materials are 3D printed using SLM technique. So here I have stated various alloys which is used in the DMLS technique, which involves aluminum alloys, stainless steel, and tool steel, which is used in SLM, and titanium alloys, cobalt, chrome, super alloys, nickel super alloys, internal material, precious metals, even gold can also be 3D printed, which is used in jewelry making. We can directly 3D print gold or very other precious metals using a metal 3D printer. Only that the source of laser adapts to the material which is used.
Hello.
So, coming to the benefits of metal 3D printer, this is used to this process is used to manufacture complex and very complex parts with difficult geometries that traditional manufacturing cannot produce. So, we go for metal 3D printing where we found using conventional manufacturing process, you cannot produce that component. You go for metal 3D printing. Otherwise, the cost involved is very high. If you can get it done in a conventional process, it is far better than going to the 3D printing metal process. And um, the physical properties or mechanical properties of a metal 3D printed part is very high when compared to the other 3D printing technologies available, like metal binder jetting technology. So the physical properties is very excellent, and the number of components in the in any assembly can be reduced using a 3D printer. That's the basic functionality of a 3D printer. You can reduce the number of moving parts or assemblies which is involved in the 3D design. So these metal 3D printed parts can also minimize weight and also minimize the number of components used in the assembly. So coming to the limitations, it's basically the material and manufacturing cost which is involved in the metal 3D printer. It is very high, and the manufacturing process is not very easy. And the build size is very much limited, and higher range build volumes are not available in a SLM or DMLS technology. And the designs with complex geometries can be easily 3D printed, and few more complex designs cannot be 3D printed, so that you cannot remove certain supports from the 3D printed part. So these are few limitations of metal 3D printing technology. So hope you had a good glimpse on the 3D printing, various 3D printing technologies available in the market. There are even more 3D printing technologies available, which is kind of new technologies are getting